Remember, for expert live tutoring in organic chemistry, email me at david.jeffrey422@gmail.com. Enjoy the video. Welcome to part 12, reaction mechanism continued. So I promised in the previous lesson that we would go through this example, and so that's what we're going to do. Well, the first step in solving any complex problem in science is to simplify it. And simplifying a problem in chemistry means putting that word problem in the language of chemistry, which is a chemical reaction equation. Now, we don't know what the products are. That's the problem. That's the challenge. But wouldn't you rather work with, right, the picture on the bottom than the words on the top? So we convert the words on the top to the picture on the bottom. And what we've done is we have converted the name of 1,3-butadiene to the structure, because you'll learn how to name compounds. We have put in the conditions, and we have spaces for 3 products, and we have the formula of each of those products. Right? So now we need to scratch our heads and propose a reasonable reaction mechanism. Well, let's take a look at some possibilities. Okay, so I'm going to give you some possible reaction mechanisms, and I'm pretty sure, I'll correct this if I'm wrong, but I'm pretty sure that in each case, all of my steps do in fact add up to the overall transformation. They're just different steps. All right, so here's a 3-step mechanism where butadiene, right, the diene, reacts with HBr in an acid-base step, right? Again, this is why we learned acid-base chemistry. HBr is a very strong acid. It is sufficiently strong to protonate the pi electrons in butadiene, and you form what's called a carbocation. It may be hard to see, but carbon 1 of butadiene on the right-hand side, the product side, has a positive charge. Right? In step 2, that carbocation then is captured by Br- to form one of the 3 isomeric products that you see there, right? Or in step 3, it rearranges. That positive charge moves from carbon 1 to carbon 2 via what's called a 1,2 hydride shift, and that carbocation can resonate and then be captured at either C2 or C4 by bromide, and so that would generate those 3 isomeric products. It would satisfy the formula for them, and so this is a plausible mechanism. Or is it? It turns out it isn't. It turns out that the first step is a bad step, and by a bad step, I mean an unreasonable, very high energy step, because you will learn that while carbocations are a very important reactive intermediate in organic reaction mechanisms, primary carbocations are too unstable. And so your professor would draw a big red line through that first step. And if the first step is bad, the whole mechanism is bad, sorry to say. Okay, so maybe this is a better first step. If the problem with the previously proposed reaction mechanism was the first step, then let's work on the first step. So again, here we have butadiene reacting with HBr, but I've turned the HBr molecule around, right? And now I've added essentially Br plus to the diene to generate the secondary carbocation. So I don't have that problem with the primary carbocation, and that's also stabilized by resonance with the adjacent double bond, right? That's a lytic resonance, right? And a co-product, according to this step, would be hydride. That's not hydronium, that's hydride, H-, right? So maybe this is a good way to start my reaction mechanism. Except it isn't. It isn't a good way, because the problem with this chemistry, proposed chemistry, is the acid-base chemistry. right? HBr is a strong acid. What do strong acids do? They donate a proton, H plus, right, to a base. I've got this reversed, right? So no, that's a bad step. Finally, I propose steps that are all reasonable, with reasonable energetics, with reasonable intermediates. Step 1, the diene reacts with HBr the way an acid-base reaction should look, right? With the diene being protonated by HBr to give the secondary allylic stabilized carbocation and bromide, right? Then in step 2, that can be captured to give one of the 3 isomeric products. You can see it there. Or that allylic carbocation can rearrange and be captured at carbon 4, and you can have both an E and Z or cis and trans product. There are your 3 isomeric alkyl bromide products that satisfy the formula. None of those steps are unreasonable. They all involve reasonable intermediates. Acid-base chemistry looks good. That is a reasonable reaction mechanism. Let's summarize in one place what a reasonable mechanism must have, characteristics of a reasonable mechanism. Okay, number 1, of course, it's got to add. All the steps must add to be identical to the overall transformation. Okay, it must explain any chemoselectivity, regioselectivity, and or stereoselectivity to be defined, right? It must agree with any kinetic data that may be available. It must not contain termolecular steps. What does that mean? Okay, in the language of chemical kinetics, you have unimolecular steps, you have bimolecular steps, you have termolecular steps. A unimolecular step, right, involves one chemical species that decomposes on its own or splits to form products. A bimolecular step involves species A and B colliding to make product C or product C and D, whatever. A termolecular step involves 3 molecules colliding. 3 reactant molecules colliding, and it's just very, very unlikely statistically that would ever happen. So we don't like termolecular steps in our reaction mechanisms, which is not to say that there probably aren't some examples. I'm sure there are, but they're very, very unusual and very, very unfavorable, and they're very unfavorable entropically. Think about that. Any acid-base steps must show either a favorable acid-base equilibria, which of course we spend a lot of time on, or if they don't show a favorable acid-base equilibria, then your reaction mechanism must allow for at least the formation of a reasonable concentration, time-dependent concentration of products that can then be driven in some way to final products. Okay, we'll hopefully look at some examples of that. And again, we saw the bottom rule: no primary carbocations, no primary radicals. Here we see some of the bad steps that we proposed earlier and why they're bad, right? Self-explanatory. This one violates that last rule. This bad first step violates the second to last rule. All right, let's take a little time and let me explain to you what this is all about. Chemoselectivity, regioselectivity, and or stereoselectivity. All right. Some chemical reactions are chemoselective. Here's an example of one. A chemoselective reaction is one that chooses one functional group over another related functional group. Okay? So what you're seeing here is the sodium borohydride reduction, right, of the aldehyde. That's the CHO attachment to the benzene ring. That's an aldehyde carbonyl in the presence of an ester carbonyl. That's the CO2 ET, ethyl ester. You'll learn that aldehyde carbonyls are much more reactive towards nucleophiles and reducing agents than are ester carbonyls. And so if we adjust the stoichiometry of the reducing agent, sodium borohydride, we can achieve chemoselectivity in the reduction of the aldehyde in the presence of the ester and not touch the ester. This is an example of chemoselectivity. In regioselectivity, here's an example of regioselectivity, and we're generally talking about stereoisomeric products. And so this is the addition of HBr to an alkene, a very important reaction for alkenes. And you can see that we can add HBr in one of two ways. We can add HBr so that the hydrogen goes to the alkene carbon bearing the methyl. That's the first product. Or we can add HBr where the hydrogen goes to the other alkene carbon. That's the second product. And you will learn that this is a regioselective reaction, and you'll learn something called the Markovnikov rule that explains it. And the Markovnikov rule, in fact, is the mechanism that explains the regioselectivity of this type of reaction. And you can see that there's about a 95-to-5 preference. And we call that selectivity. Once you get around 98-to-2 or 99-to-1, we start calling that regiospecificity. So if you see selectivity versus specificity, it's just a matter of degree. This is regioselectivity. Here's another example of regioselectivity in a thermal Diels-Alder reaction, which is a reaction between a diene, which you see as a reactant A, right? And either an alkene or an alkyne, in this case an alkyne. And this is really head to tail or head to head. So actually I should qualify what I said before. The products of regioselectivity don't necessarily have to be stereoisomers. They were in the first case. Here, of course, they're constitutional isomers. And there's a 99-to-1. And this is actually real data. There's a 99-to-1 preference for the top versus the bottom, and you'll learn why when you actually take organic chemistry as a course. And this probably would be called regiospecificity. I mean, 99-to-1 is pretty darn good. Well, here's an example of stereoselectivity, and obviously in stereoselectivity we are talking about differences in stereoisomers, either relative, which is generally the case, relative stereochemistry, or occasionally absolute stereochemistry, but your proposed reaction mechanism must accommodate either if it's observed. In this case, we have a difference in relative stereochemistry between the two products. And what we have here is we have a bromoalcohol as a reactant, reacting with LDA, which is lithium diisopropyl amide, which is a strong base. And of course, we look for the most acidic hydrogen in the reactant, which we learned how to do before. That would be the OH hydrogen. That hydrogen gets removed and forms the O- conjugate base. And that O- conjugate base attacks the carbon bearing the bromine from the back side. Why? Because that's the mechanism of that reaction. And that's why we get a 96-to-4 ratio of the backside attack, the first product, versus the front side attack, the second product. Remember, for live tutoring in organic chemistry, just email me at david.jeffrey422@gmail.com. I hope you've enjoyed this video.